Okay, so we just looked at this example, and we saw this graph, which tempts us to say that the limit of this function, I'll just call it f, this is f, as x approaches 1 is going to behave the same way as this function did. Because this function and this function are the same everywhere except at x equals 1. So the closer we get to 1, they'll still behave exactly the same way. The only difference is that this function is not defined at 1 and this function is. But everywhere else except for that one place, they behave exactly the same way. So we can say that this limit, let me write it over here, is equal to the limit of 1 over x plus 2 as x goes to 1. And that is easy to see what that will be. Well, basically we see that it's going to be 1 over, we can just replace 1 in here, and we get 1 plus 2, or 3. Okay, let's take another example. Let's try, suppose we're interested in this one, the limit as x squared minus 4 over x minus 2, as x approaches 2. So this is the same basic situation as we had before, because when you replace 2 in here, in both places, we again get 0 over 0. So this function is not defined at 2. However, we can say that x squared minus 4 over x minus 2 equals x minus 2, x plus 2 over x minus 2. And then we can say that equals, we can cancel this and this, that equals x plus 2, except when x equals 2. So everywhere else, this is equal to this. Now this concept of limit is really asking, what is this function getting close to as x approaches 2? So let's explain that a little bit more first, and then we'll come back to this problem. So here's one way to think about what the concept of limit is. So it's kind of like a game. So the game is that, suppose I will answer any question you want to ask about a function. So I have this function. Let's say I secretly have this function, x squared minus 4 over x minus 2, and I'm kind of hiding it, so you can't see it. You can't see this function. And and your job in this game is to tell me what the value, remember what we mean by value, it means the height, what the value of the function is when x equals 2. So that's what you have to do in the end, is tell me what you think the value of the function is, in other words, what the height of the function is when x equals 2. And the rule is The rule is you can ask me about the value of the function anywhere except for 2. Okay, so you can and then your job is to guess what it is at 2. So that's the rule. So, of course, you're going to say, okay, you're going to say, well, how about when x equals 3? So I have to tell you that. So I'll put 3 into here, and let's see, what would I get? I'd get 3 squared minus 4 over 3 minus 1. So I would get 9 minus 4 over 2. So I would get, sorry, it's 3 minus 2, so it's 1. So I would get 5. Okay, so I have to tell you that. So you'd say, what's the value of the function at 3? And I'd say 5. Then but your job is to guess what it's at 2. So you're not going to leave it just at 3. You'll say, okay, well, what is it at 2.5? And then I have to tell you, so I have to do the calculation. Maybe it turns out, I'll just make it up right now. Suppose it turns out to be 4. And then you say, okay, well, what is it at what is it when x equals 2.4? And I have to tell you. And then you say, okay, what is it when x equals 2.1? And I have to tell you. And then you say, well, what is it when x equals 2.01? And I have to tell you. And then you'll say 2.00001. And I have to tell you that. And then once you get tired of keep asking, then your job is to make a guess about what it's equal to actually at 2. So that's what the limit problem is about. So when we write this, the limit as x approaches 2 of this function, what was it? X squared minus 4 over x minus 2. You can think of it as like this game, and it's what you would guess if you kept playing this game and kept asking me values that are closer and closer to 2, what you would guess that was equal to. That's what we mean by the limit. That's what we say the limit is equal to. What you would guess as you kept going down, getting closer and closer to 2, and you could also choose values that were below 2. So like you could say, okay, what is it when x equals 1, and then 1.5, and then 1.1, and then 1.0, sorry, what am I doing? 1.9, and then 1.99999, and so on. So you could get closer and closer to 2 in this direction. You could ask those questions as well. And then finally, you're going to make your guess. And that's what the limit is basically equal to. It's what you would guess if you played this game. Okay? So, going back to this question here, we know that this x squared minus 4 over x minus 2 is equal to x minus 2, x plus 2 over x minus 2. And that's equal to x plus 2 as long as x is not equal to 2. So that means that this behaves like this, except precisely at 2. But as close as you want to get to 2, it behaves the same. So if you want to know what's happening to this as x gets close to 2, you can say what's happening to this as x gets close to 2. And that's easy. What's happening to this expression as x gets close to 2? It's obviously getting closer and closer to 4. So then the limit of this is going to be 4. Okay? So we can play this kind of game here, and we can do these kinds of tricks here, some algebraic tricks, to make this thing simpler, and then say that the limit of the simpler is the same as the limit of the original, even though the two are not equal at the point where we're interested. Even though they're not equal at 2, but near 2 they are equal. The only place where this and this are not equal is when x is precisely at 2, because this just isn't defined yet. So what that means is, in terms of the picture, by the way, is what does the graph of this look like? It looks exactly like the graph of this, because this is equal to this is equal to this, except when x equals 2. So except at x equals 2, I forgot to say that, except at x equals 2, the graph of this and the graph of this are the same, but the graph of this is simple. The first example we looked at wasn't quite as simple. It looked like this, which isn't quite as simple as this one. This one is quite simple, just y equals x plus 2. What's that look like? It has a y-intercept at 2, and it has a slope of 1. So, and when x equals 2, it's about 4. 4 up here. Can I draw this right? So it's about like that. So this is supposed to be 4. But anyway, that's what this looks like. So what does this look like? It behaves exactly the same as this, except at x equals 2. Let me get rid of that. I can. There. Oops. Okay. So actually what I want to do is take the eraser, and right at 2, I want to put a hole. I can't do that, I guess. So I can't do it properly with this eraser, but I'll just do it like this then. So there's this circle there. There's not supposed to be a line in there. It's a circle. So it looks like this. Like that. So, so the graph of this is exactly the graph of this, except when x equals 2. So everywhere else it's just a straight line, and at 2 it just has an open circle like this. Okay? So, and then, so the limit of this is 4 as x approaches 2. So again, we write the limit of this function. I'm not going to write the whole thing again. As x approaches 2 is 4. So that's how we use this limit notation. Okay, let's try something else. Let's take that same function, which was x squared minus 4 over x minus 2. And let's make a new function. Let's call this new function g of x. And let's use this kind of idea. So what do I mean? I want to define a piecewise function, and I'm going to use this formula for all x except when x is 2. So for any x not equal to 2, I'm going to use this formula. So in other words, again, it's going to be that straight line, but at x equals 2, I'm not using that formula, so I don't know what to put there. But now I'm going to give a separate value when x equals 2. So when x equals 2, I'm going to tell you what to do. So remember, this was 4. So I'm going to make it, let's say, 3. So what does this look like? So it looks exactly like the straight line that we saw before, except we still have this, I have to put a circle here. And then when x equals 3, let's say this is 3. It doesn't look like 3, but suppose that's 3. So here. So this is the picture. So first of all, is this a function? So what does that mean? Well, basically it means, does it satisfy the vertical line test? So if you draw a vertical line here, 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 is there anywhere you can draw a vertical line and cut the curve in 2 places? The answer is no, there's no place. Even here, if I draw a vertical line there, whoops, that didn't work very well. Let's see if I can do that with this. Even here, if I draw a vertical line, I only cut it in one place. So anywhere that I draw this vertical line, it only cuts the curve in one place. So the answer is yes, it is a function, right? So this is a function. And now I can ask the limit for this as well. For example, I can ask the same question as before. As x goes to 2, and what's the answer? It's the same answer as before. As x goes, it doesn't matter what happens exactly at 2. It's just what happens near 2. That's what the limit is asking about. Not exactly at 2, but near 2. So near 2, it's getting closer and closer to 4. That doesn't mean that at 2, it's equal to 4. So this is like an extra tool that we have now. The limit is kind of like an extra, like a hammer that you have, a special hammer, a special tool that you can ask about functions when they get close to a certain place, as opposed to asking what happens right when they are at a specific point, right when x equals 2. That's a different question than asking what happens as x gets closer to. So it's just like an extra tool. So maybe you don't need it most of the time, but to have it is not a bad thing. So if you want to know what's happening close to 2, then you can talk about the limit. If you want to know exactly at 2, that's a different question. That's saying, what is f of 2? Or what is g of 2? That's a different question than what's the limit getting close to 2. So here, the limit getting close to 2 is 4. But the actual value at 2 is 3. There's 3. So there we can see that they're different questions. So what's happening exactly at 2 is one question. What's happening near 2 is a different question. So the limit is a kind of extra tool that allows you to answer or ask those kinds of questions. What's happening as you get close to something. Okay, here's an unusual function. So this is y equals the sine of pi over x. This is kind of a weird function. I think we saw somewhere in a previous discussion that when we look at something like y equals the sine of 6x, or let's make it easier, I think we looked at y equals the sine of 2x, that whereas the sine function looks like this and goes through a full cycle in 2 pi, that if we look at 2x, that it doesn't take 2 pi to get through the full cycle, because when x goes from 0 to pi, the argument goes from 0 to 2 pi. So actually, this looks like this. So it only needs pi in order to go through a full cycle. So that gives us an idea of what's going to happen here, because when x gets smaller and smaller, so as we move to the right, what happens to this? We're getting pi over, say, 2, then we're getting pi over 3, pi over 2, then pi over 1, then pi over 1/2, then pi over 1/3, and pi over 1/10. So what's happening? When we take pi over 1/2, that's equal to 2 pi. When we take pi over 3, that's equal to 3 pi. When we take pi over 10, that's equal to 10 pi. So the same kind of thing that we saw here, which was kind of shrinking the period, is happening sort of more and more. So the period is shrinking more and more as x gets closer and closer to 0. And so this thing is jumping up and down, and you can see that basically it's going to jump up and down infinitely as x gets closer and closer to 0. So if you believe that, then if we ask, what's the limit of this function? What function is it? Sine of pi over x as x gets close to 0. So that's kind of a weird question. But the answer is that, does it ever approach a number? No. So one of the things about limits is that, for example, when we looked at the last example, that was x minus 4, and this was x minus 2, one of the things there was that we have to get a single number as the answer. So we didn't stress that, but remember the picture looked like this. And we only would have guessed, there's a single number that we guessed 4. So you can't have many different numbers. You can't be approaching many different things. Then we say, if it does that, we say the limit doesn't exist. So here, since it's constantly jumping up and down, you can't say, oh, it's always getting closer to whatever this number is, 0.2, or oh, it's always getting closer to 0.5, or oh, it's getting closer and closer to 0.9. No, it's jumping up and down infinitely many times, so it doesn't get close to any single number. We can say it's always between -1 and 1, but we can't point to a specific number that it's getting closer to. So in that case, we say the limit does not exist. I'll use DNE, but the limit does not exist. Okay, so for this case, when x gets closer to 0, we say this, the limit doesn't exist. Now, if we look at some other number, like if we ask what happens to this as x gets closer to 1, not 0, then it's right here. So we can see what is the height there. It's 0. So the answer would be, as x gets closer to 1, the answer would be 0. But we're not asking at 1. We're asking at 0, as x gets closer to 0. And there we have to say this, the limit does not exist. Okay, next let's look at this. Now, is this a function? What about this one? Is this a function? The answer is yeah. Again, the vertical line test, you can't cut it in more than one place. Right here, when you cut it here, you only hit 1. You don't hit this. This is an open circle. So let's write this as a piecewise defined function. Let's call it h of x. It has a name. It's called the Heaviside Function. That's somebody's name, Mr. Heaviside. But anyway, let's write this as a piecewise defined function. So we can see that we can split it up into 2 domains. It behaves differently to the right of 0 than to the left of 0. So let's say when x is greater than 0, but actually it's better to say when x is greater than or equal to 0. But anyway, let's start with that. When x is greater than 0, it's always equal to 1. And when x is less than 0, it's always equal to 0. That's the height. The height is 1 when we're to the right of 0. The height is 1. When we're to the left of 0, the height is 0. So this is it, except we need this here too. Right? So we use this even when x is equal to 0. We use 1. Okay, so this is called the Heaviside function. Now, so remember, we said that for a limit to exist, you have to get a single number. Now, the example we looked at before, that crazy-looking kind of sine function, that was much more complicated than this one. So this one might be better to explain this idea that you have to get a single number. So let's call this, we called it h, so let's say h. And suppose we ask, as x gets close to 0, what's the limit? But the part of the definition of limit, we haven't really written clearly what the definition is, but part of the definition is that whatever number you give, there has to be only one number. It can't be a couple numbers. So what would you say here? So as you get closer and closer to 0, like here, suppose this is 1, and this is a half, and this is a third, and so on. So as you get closer and closer to 0, each time you play that game, I have to say, oh, it's 1, it's 1, it's 1, it's 1, it's 1, it's 1. So what are you going to guess in that case? You're going to guess, oh, it's equal to 1. But if you had played the game over here and said, what is it here? What is it here? What is it here? You know, and I'd have to say, oh, it's 0, it's 0, it's 0, it's 0. So if you guess coming in from the right, you're going to guess 1. But if you had guessed coming in from the left, you're going to get 0. So we don't get the same thing on both sides. So neither is right. We say the limit doesn't exist, does not exist. Okay? So if you don't get a single number, you have to do this. It doesn't exist. Because when we say a limit, we mean a single number. So if there's not a single number, then there's no limit, we say. Okay? So that's the idea of the limit. So that leads us to say, well, that's kind of a limited tool now, because I can only say it doesn't exist. That's sort of like, why can't I explain a little bit more about this picture than just saying, oh, the limit doesn't exist? That's kind of limiting. That's a kind of pun. I don't mean the pun. But that's kind of like restrictive. Why do we have to be so restrictive in this definition? Why do we have to say, oh, just does not exist? I'd like to be able to report back a little bit more information than just does not exist. What would I like to be able to say? I'd like to be able to say that the limit of this function, and then I want to say, as x gets close to 0 from the right, so if I can write that all down, then I can say, I can say 1. If I'm only coming in here, I can say 1. So this gives more information than just saying it doesn't exist. This says, yeah, it doesn't exist, but if you restrict yourself only coming in from this direction, it's equal to 1. So that's, if you want a tool, why not have this as well? That is, be able to say just as you come in from the right. And of course, you could also say the limit of h of x, and then you have to write all that stuff, but coming from the left, and then you could report, oh, but that is equal to 0. So these are extra tools that we could develop that would allow us to give this information as well. So we'd still say the limit does not exist, but we'd say, but on the other hand, when you get close to 0 from the right, it's getting close to 1, or it is 1, and coming in from the left, it's 0. So why not develop that or have some notation for that? And the notation, I prefer to do this one more time. Let me make this picture. So let's put this here, and this is 1. And let me put over here a different graph, different function. Let's say this is at 8. Okay, so at 8, it jumps up. So the function is defined differently now. It's at when x is greater than or equal to 8, and when x is less than or equal to 8. So suppose we had that function. So what would we say? Using this notation, we would say the limit, we're talking about as x gets close to 8. Again, this limit does not exist, is the way we usually write that. But we want to say something else. We want to say as we get close to 8 from the right, then we're going to say for that, as we get close to 8 from the right, we're going to say what? It's 1. Now how do we write as x gets close to 8 from the right. Well, we don't want to write out that whole sentence there, so we just write it like this. As x approaches a plus. That means from the right. Maybe they should have, I think it would have been better to have this notation. Limit as x approaches a from the right, but nobody wrote that notation, so they wrote plus instead. So anyway, that's what the plus means there. And then we can also do, of course, the limit as h, a limit of h as x approaches a from the left, and that is 0. So this gives us some extra information. Now we can write this plus, this minus, and we can give information. So we can still say this, the limit doesn't exist, but we can also say, but if you come in just from the right, you will always get 1, or you will be getting closer. By the way, it's a little bit weird to say it's 1, because it's a little bit weird to say it's getting closer and closer to 1. It's actually equal to 1 the whole time. But if we had a picture like this, so at 8, suppose it looked like this. Here's 1, and then we had this, that. By the way, I drew this wrong, right? I should have had open here and closed there. But anyway, I'll leave that. And let's say we had this, or this rather. So, or whatever. So here we'd say, oh, it's getting closer and closer to 1. It wasn't equal to 1. Here it's always equal to 1. So it sounds a little bit strange to say that it's getting closer and closer to 1 when it's actually equal to 1. But anyway, ignoring that problem, as x gets closer and closer to 8, it's 1. And as x gets, from the right, it's 1. And as x gets closer and closer to x from the left, it's 0. So now we can say all 3 of these statements. That gives you more information than if I just told you this. If you couldn't see the picture and I just told you this, that wouldn't tell you as much as if you couldn't see the picture and I told you all 3 of these. So why not have all 3 of them? Okay, so now we have this way of denoting from the right and from the left. Now I didn't want to do it up here when we had the other function, wherever it was. Where was that function? Here. Because it looks confusing. Because we would write, in this case, for this h, we would say the limit as h of x as x approaches 0. From the right, we write 0 plus. So that makes you think that when you put a plus up there, you just mean the positive numbers. And that's not what the plus means. It means to the right. But in the case when it's 0, being to the right and being positive numbers is the same thing. So it's a little bit of a bad example to use this notation for the first time with this example. Because when you write 0 plus, you think, oh, that must mean positive numbers. It doesn't mean positive numbers. I mean, in this case it does, but in general it just means to the right of whatever we put here. So if we had 8 plus, it means to the right of 8. If we have 8 minus, it means to the left of 8. So these are called one-sided limits. And we call the one from the right, so the limit of some function f as x approaches some value a from the right, we call that the right-handed limit. At, I guess maybe at x equals a, the right-hand limit at x equals a, and this we would call to some a, as it approaches some a, we call it the left-handed limit, the left-handed limit.